Hey everyone, and welcome back, puzzle solvers. I am absolutely thrilled to have you here for today's explainer. Today, we're going to look at something that might just completely change the way you view mathematics. Seriously, we are going to treat mathematical proofs not as those dry, dusty textbook exercises you might be used to, but as thrilling, high-stakes detective puzzles. I want you to imagine every single shape as a crime scene, and every given number as a crucial piece of evidence just waiting to be decoded. If you love a good mystery and you really enjoy cracking a logical sequence, you are going to absolutely love this journey. Just think about that for a second. If you only know a single solitary angle inside a rectangle, can you logically deduce every other hidden angle inside the entire shape? I mean, is one clue really enough to unravel the whole shebang? Okay, let's dive into this and see exactly how it's done.
Section 1. The Quadrilateral Angle Mystery. Investigating the Scene.
Now, when you first look at this geometric setup, it looks, well, completely chaotic. We've got a rectangle intersected by diagonal lines, which creates this incredibly complex web of triangles filled with unknowns. We're talking angles numbered 1 all the way through 12. It feels super overwhelming at first glance, but as with literally any good mystery, we just need to break it down.
So to crack this, we got to pull out a couple of trusted tools from our source material. First up is the law of vertically opposite angles. We know that when two straight lines cross, opposite angles basically act as mirrors. They are mathematically identical. So if one side is 110 degrees, the opposite side is exactly 110 degrees, no exceptions.
Second tool is the linear pair. We know adjacent angles along a flat intersecting line always sum to exactly 180 degrees. And honestly, that's it. Those two fundamental definitions are really all we need to crack this case wide open.
Let's take a look at our very first official piece of evidence in rectangle ABCD. We are given one single clue. Angle 1, down there in the corner, is exactly 30 degrees. And it's wild, but from this one tiny thread, we can completely unravel the entire shape.
Just watch how this logic cascades. A rectangle's corner is 90 degrees, right? So angle 2 has to be 60. Super simple. But the source reminds us of a really crucial property here. A rectangle's diagonals are equal and they bisect each other, forming isosceles triangles. Because isosceles triangles have equal base angles, that 30-degree angle perfectly mirrors right across the base. Subtract those two 30-degree angles from the 180 degrees of a triangle, and what do we get? We're left with exactly 120 degrees for that top central angle. Boom! 120 degrees. Discovering this linchpin just breaks the rest of the puzzle wide open. It's a really great reminder of how uncovering just one hidden variable in a logical system can cascade into total clarity. Because from here, we can use our vertically opposite and linear pair rules to instantly fill in the rest of the center and cascade that logic right back out to the remaining corners. It is so incredibly satisfying to watch unfold.
Moving right along to Section 2, cracking rectangle angles working backwards.
But what if we completely flip the script? Let's consider rectangle PSRQ. Our starting clue is completely different this time around. We don't have a nice, neat corner angle. Instead, our only piece of evidence is sitting right dead in the middle. Central angle 9 is 110 degrees. So the question now is, how do we work backwards from the center to find the outer corners?
Applying the reverse method, we just use those exact same trusted rules. Vertically opposite means the bottom angle 11 is also 110 degrees. The linear pair rule tells us the adjacent angle 10 is 70 degrees. Now looking at that bottom triangle, if the top is 110, we have 70 degrees left. Because those bisecting diagonals give us an isosceles triangle, we just split that remaining 70 degrees perfectly in half.
Which leaves us with exactly 35 degrees. This brilliantly illustrates the sheer power of deductive reasoning from the inside out. By pinning down the center of the system, the outer edges naturally reveal themselves. We literally solved the whole shape in reverse.
Section 3. Drawing from diagonals, the architect's blueprints.
Now we're shifting gears from breaking down existing shapes to actually acting as architects and constructing entirely new ones based on the textbook's second question. The source material gives us strict construction parameters to draft our new quadrilateral blueprint. First, we're told to draw a line segment of 8 centimeters. Then we bisect it perfectly in the middle at 4 centimeters. Finally, we draw a second 8-centimeter line through that exact midpoint, but intersecting at a very specific angle. Now, if you intersect those diagonals at, say, a 30-degree angle versus a 40-degree angle, you can immediately see how the shape's proportions shift. One is stretched out,
while the other is visibly taller. But despite this huge visual difference, they share an unbreakable geometric truth. Here's the big reveal. Because the diagonals are equal and they perfectly bisect each other, the resulting shape must always be a rectangle, regardless of the intersection angle. I mean, no way, right? It's an incredible mathematical truth that forms the very basis of architectural stability. If you lock in your diagonals, your structure will always hold true.
Finally, Section 4, the parallel properties proof, closing the case.
To officially close the case, the source outlines this absolutely beautiful, definitive proof using transversals. So we know a quadrilateral's total angles sum up to 360 degrees. But look at what happens when we focus on the parallel nature of a rectangle. Adding just the same side interior angles together gives us exactly half of that, 180 degrees.
Let me read this definitive proof directly from the text, because it's absolutely crucial. Since line BC is a transversal to lines AB and DC, and the sum of interior angles on the same side is 180 degrees, therefore lines AB and DC are also parallel. This is the core geometric law that dictates exactly why these opposing lines will extend into infinity and never, ever cross.
And that leads directly into our final verdict for this geometric detective case. The text concludes, hence, both pairs of opposite sides of quadrilateral ABCD are parallel, therefore, ABCD is a parallelogram. We have proven, without a shadow of a doubt, that geometrically speaking, our rectangle is definitively a parallelogram.
So I want to leave you with this final provocative thought. If we just mathematically proved that a rectangle is a parallelogram simply because its opposite sides are parallel, does that mean every parallelogram is also a rectangle? Think about what happens when those nice, neat 90-degree corners start to tilt. Thank you so much for joining me for this explainer. Keep questioning the systems around you, and I will absolutely catch you on the next deep dive.